We're doing one for equal 6.
We are going to just fill out the table and all right. So last lecture we developed a table to do the trapezoidal rule. Here is the formula for the here is the integral that we are trying to evaluate, and we did evaluate it using multiple applications of the trapezoidal rule, or basically like multiple segments. And no need to write for a minute. Please listen. Please look up. Please listen. Then you can doodle with your computer. So the starting point is A, which is 0 in this case, and the limit, upper limit, is pi by 2 or 1.57 to 4 decimal points. And then we are going to do six segments, or first we'll see the solution for 10 segments, and you get the values of x starting from 0 all the way to, starting from 0 all the way to 1.57. So that is divided into 10 segments or 11 points. So 0 to 10 is 11. Okay, 11 segments, 10 points. You compute the value of the function at each of the x values, and then there is a weighting factor which corresponds to the trapezoidal rule that we talked about. So we multiply w and f of x, you get this column, you do the summation, and then what is the trapezoidal rule formula? I trapezoidal rule is b minus a over 2n multiplied by f of x naught plus I equal to 1 to n minus 1, f of xi, silence please, plus f of xn. This is your trapezoidal rule formula. In our case, say n equals 10, a equals 0, b equals pi by 2, and we are doing this summation here. So when I say weighting factor, this is multiplied by 1, and this is multiplied by w of x naught, w of xi, and again this is multiplied by 1, which is w of xn. That is what I'm showing here. First row 1, last row 1, everything in between 2. That is the formula that we have here. So you do the summation. This portion is what I call as the summation here. So this portion is wxi multiplied by f of xi for I equal to 0 to n. Okay, and then if you put it in Excel, the value we get is 12.4186 for 10 segments using the trapezoidal rule. Okay, so this was all what we did last lecture. So today's class participation exercise is for you to take a sheet of paper, put this table with 6 entries. What is I trapezoidal rule 10 segments? It's the number you got from your Excel sheet. Put it down here, which is 12.4186. 12.4186. Okay. Instead of 6 segments, I'm just going to make it like 3 segments so that people can do this on hand. For those who are not doing it with the computer, you can still do this in hand. So if I have 0 and pi by 2 and I need 3 segments, how do I divide this? I need to divide this as pi by 2 minus 0 divided by 3, or in steps of pi by 6. So 0, pi by 6, pi by 3, 2 pi by 3, and is this correct? No. Okay. What should be the third?
4 segments?
Oh, we need 3 segments. Sorry. Three segments. So you need 1/3 and then 2/3. What is 1/3? that is pi by 6. Right? And then 2 pi by 6, which is pi by 3, and 3 pi by 6, which is pi by 2. So compute f of 0, f of pi by 6, f of pi by 3, and f of pi by 2. Compute those values, those who are doing it manually. Then you would do this I 3 segments is pi by 2 minus 0 divided by 3 then multiplied by half. F of 0 plus 2 times f of pi by 6 plus f of pi by 3 plus f of pi by 2. Compute this and tell me the answer and put it here. If you're punching it in your calculator, common mistakes are not checking for degree and radian. Okay, make sure that pay attention to. I'm just modifying my spreadsheet to reflect 3 segments so that I can have the answer. So it's good practice to do this because in the exam, a realistic problem would have 3 or 5 segments, not like 20 or more segments, not like that many number of segments. So good practice to try. Are you getting 13.9267? I'm going to put it. I'll wait for you to confirm it. $13.9267. So there is no excuse today. Either you do it on laptop or you do it on paper, but you're doing it.
Do you want us to list the errors like that?
Yeah, sure. If you want to, I'm not asking, but at least I'm going to use this to make a point.
If we,
So,
I'm sorry to trust you again, but if we do it on a computer, can we write our answers?
yeah, if you are doing it on the computer, you copy your answers. That is kind of how you would do it in the exam.
Yes.
Use the Excel, but fill out on the paper. Remember, we won't grade your Excel sheets. Are we getting 13.9267?
Yes.
More responses from
Yes.
other people. Are you getting 13.9267 for 3 segments? Yes, no. No. What is, where are you start?
I got 11.78. I probably did it wrong.
Did you, I can tell you these values to cross check. Okay, what is f of 0? 6. What is f of pi by 2? I'm sorry, f of 0 is 9. F of pi by 2 is 6. What is f of pi by 6? Pi by 6 is 8.9631. 8.9631. And f of pi by 3 is that is 8.5981 and then 7.5. 8.5981 and then 7.5. So if you have these numbers, you plug them in. What happens later that is arithmetic. I hope you can do that. Yes.
I'm getting 12.356.
12.3556 is in. Okay, so let me check my spreadsheet here. So your step length is pi by 3, right? Pi by 3, and my exact segments is half times summation. Oh, okay. I have to change my weight. 12.3559, right? I made a mistake. 12.3559, and the error, how will you compute the exact error? It's just one absolute error is equal to 1 minus I numerical, or the estimate you get from a formula, divided by I exact expressed as a percentage. All right, time to move on. So is everybody having these two values start now? Because all this is just recapping what we did. Okay, now we're going to learn two more formulas: Simpson's rule, 1/3 rule, and 1/3/8 rule. So the main conceptual leaf now is when you had the trapezoidal rules. When you had the trapezoidal rule, you have a curve, and you divided that into trapeziums, and then you try to sum up their areas individually, and you get this representation. So if you have, say, n segments, you have n segments, 1, 2, 3, n segments, you are getting the value of the integral as the sum of the areas of each of the segments. Now, not all functions are well behaved like this. Not all functions just smoothly increase or smoothly decrease. They have a lot of these increases and decreases, or what is called as non-monotonic behavior. They don't simply just increase or decrease. They sometimes reach a peak, come down, again increase, and so on. So when you have these kind of functions, your error with trapezoidal rule could be considerable, because trapezoidal rule often ignores this change in curvature. It approximates the curve as a straight line. So to counter that, we have other methods. So Simpson's 1/3 rule. There is a derivation to it which is kind of lengthy, which I'm not doing. What I'm presenting here is a formula. I want you to compare this formula and the formula that I'm about to write, and see how you just have to readjust your thinking a little bit. Okay, so let's write down the formula here first. B minus A, or 1/3 B minus A over N multiplied by f of x naught plus summation I odd, meaning I equal to 1, 3, 5, 7, and so on. The odd points we multiply by 4. F of xi we multiply by 4, and the even points, so we'll say j even, j equal to 2, 4, 6, 8, and so on. We multiply by 2 plus f of xn, f of xi plus f of xn. So this is the formula for Simpson's 1/3 rule. No need to write it down, I'll give you time, but try to compare how they look different from the trapezoidal rule. You have the first and last term, the weightage of which is 1. And the intermediate terms all have a weightage of 2. Here, same thing about the first and last term, W. But if I try to generalize this and write Wi xi from I equal to 0 to n, I can generalize this by writing W of x naught equal to W of xn equal to 1. The first and last terms have weightage of 1. All the odd terms have weightages of 4, and all the even terms have weightages of 2. So if you are doing 3 segments, this is first, this is last, this is 1, which is odd, and this is 2, which is even. So you would modify this with Simpson's 1/3 rule. Okay, now I'll stop and give you time to catch. For those who are doing it manually, I'm going to keep the 3 segments. You are going to need the value of the functions at these points, which we already have. The only thing that's going to change is the weightages of those points. So previously, when we did trapezoidal rule, the n equals 1 and n equals 2 were weighted as 2. Now they are going to be weighted as 4 and 2 respectively. So let's redo the calculation. Let's redo the calculation. So I 3 segments, Simpson's 1/3 rule. We are going to have f of 0 plus 4 times f of x1, which in this case is 5/6, plus 2 times f of x2, which is 5/3, plus f of xn or x3, which is equal to 5/2. So imagine this is an exam. Punch in the numbers and tell me what I should write here. And the percentage. Now, when you do this, make sure you have the 1/3 factor and not one half. This is 1/3, okay? Or I remove this. 1/3, and then this n is n equal to 3, or this 3 is n equal to 3. Hmm. 4, 2, right? P minus A divided. So what are you getting? Yeah.
11.2386.
11.2386.
9.55% error.
So I'll wait one more minute for others also to tell me if they are getting the same. You're getting?
That's it.
Okay. Okay, good. Looks like people are getting the same thing. So, from the context of preparing for your exam, it's really important you be able to do these type of hand calculations, because when you use the software, you still have to remember what the formula is so that you can punch it in correctly. So I'm going to bring down the screen and show you the calculation for 10 segments. Okay. Before I do that, let me just, yeah, all right. All right. So listen, take a pause, listen. So this was our spreadsheet when we did the trapezoidal rule. It still has some common features, like for example, we still have a to B, and we have a step length which is B minus A divided by N. What's wrong with this? Okay. All right. Can you please stop? Disturbing. Sorry. So this is 10 segments, trapezoidal rule, it still hasn't been modified. I have step length b minus a divided by n, and I'm using 10 segments, so 0.1157 is my step length. I'm going to change the weights corresponding to Simpson's 1/3 rule. Okay, Simpson's 1/3 rule. And the weights here are in column H. All odd terms are going to be 4, all even terms are going to be 2, which of course you can do manually. But it's not a gigantic leap for you to write a program or like a short statement in Excel, right? If this column here, column E, is odd, how do you check if this is odd?
By 2, you get a whole number or not.
So you have to come up with this, the words that are written here is logical test. You have to come up with a simple statement in Excel that checks whether a given number is odd or even. Okay, so if you do that, if it is odd, it's going to be 4. If it is even, it's going to be 2. Okay, so I off the top of my head, I don't know how to check that. So, but I'm going to check if even odd, is that the name of the function? Okay. So let's check out this odd function. No, this is not what we want. We want to check if something is odd or even. Check odd. No. Okay, let's not waste time here. So I'm going to take my I equals 1, enter it 4, I equals 3, and then 5, and then 7, and then 9. And then for even values, it's the weightage is 2, so I can leave it as such. And the summation comes out here 237. Okay, but my I10 importantly has to have 1/3 and not 1/2 in the formula. So here is my table where we have the f of x value at each x value, the corresponding weightage. This column here is the product of f of x and w of x. So if you see here f of x, w, weightage times f of x, the summation of that. So if I click this, this is nothing but the summation from x equal to I equal to 0 to I equals 10. And then next line, I put here 1/3 of the summation multiplied by my step length. So B6 is my step length, and then I14, B6, I14 is my summation. That is basically this term here. Whatever appears within the square bracket, that is this summation. And then my answer is this I10 segments. So I get 12.4248, which is pretty close to the exact value within numerical error. And the absolute error is almost 0%. Okay. So what I want you to do is, those who are trying it on Excel, do this, grab this value, put it on your sheet. 12.4248. So I'm generating this file and I'll upload it at the end of the class. Now remember, in the exam, you have access to any information that you want, including this information. So the very least you could do is at least grab these files, use it in the exam for the problem that is being asked, and you can at least solve it. So 1 second. So there is a lot of information that I'm allowing you to access. All I want you to show is that you can apply these formulas and do calculations. Yes.
Do you not have to change the f of x I to 1 minus e to the negative 2x?
Why 1 minus e?
That's what on your Excel you got.
No, 6 plus 3 cos x. That's the problem we are doing right now. So, yeah, maybe you are referring to another problem. So, see, these changes I am making right now. So, maybe if you downloaded it now, it might not be there. All right, so 12.4248, grab it and put it in your table. $12.4248, which is like 0.00%. You have to use only 2 decimal points. Okay. So now, any questions at this point before I go to the next form? That is the reason I put emphasis so much on the weightage is that it will allow you to quickly go from method to method without having to memorize different formulas. Okay. I mean, at the end of it, I'll write a summary for how W of X looks like for each method, but you get the point. It's the only thing that changes from method to method. If you keep the number of segments same, the same code or same routine of calculation can be used to do either trapezoidal rule or Simpson's rule or Simpson's 382. Okay. So this is our Simpson's 1/3 rule. Now we'll write out 3/8 rule, which also looks like this. So Simpson's 3/8 rule, Simpson's 3/8 rule changes in only one place. Okay. Instead of this factor 1/3, we are going to have b minus a divided by n f of x naught plus 3 times the intermediate terms summation f of xi from I equal to 1 to n minus 1 plus f of xn, the whole thing divided by 1 over h. It's not 3 over 8. 3 is multiplied only with the intermediate terms and not with the end terms. So, Simpson's 1/3, 3/8, trapezoidal, all of these rules are summarized in table 21.1, which includes other higher order formulas too, but we'll focus only on the first 3, namely trapezoidal rule, Simpson's 1/3 rule, and 3/8 rule. So now, very small modification. Redo the calculation for 3 segments and please put it here. B minus A divided by. Plus 3 times sequences E minus A divided by N is this, that is by 8 into summation. Oh, wait, I think you're right. Oh, if I check this formula. I think it's because we did. So if we do P8. Yeah. Where did that be? So what are you guys getting?
I have a question.
Yeah,
Did you mean to write 1/8 with this supposed to be 3/8?
I meant to write this whole thing divided by 8, which I wrote like this. And this B minus A divided by N in our case is N is equal to 3. So this is the step length. So if you had 10 segments, this would still be the step length multiplied by this summation, where the first and last have a weightage of 1 and intermediate points have a weightage of 3. That is my understanding of the formula, but I'm not getting the answer right. I don't know what you guys are getting. Yeah, same thing I'm getting. So I'm wondering why.
I mean, if you multiply that by 3, then you get to the 12.
I agree that you will, but let me also share my dilemma with you. So this is the formula. Let me make this bigger. So this is Simpson's rule, Simpson's 3/8 rule. And here is the formula they give for a range which is divided into 3 segments. Here it goes. 3h, and in this case, h is equal to b minus a divided by 3. All right, so in that case, I can now multiply this by 3. And that gives us 13.52. This is for 10 segments. For 3 segments, we get 12.4277, 427 each, or 12.4278, and an error that is 0.02%. So grab these two values if you're doing it on Excel or if you do it on paper, get these values and let's put it in our table.
So would this be a thing where we want to do yes?
So I'll put this value first. 12.4247. And the error is minus 0.03%. And if I do this with 10 segments, I'm getting 13.5291. Somebody needs to cross check me.
I got the same one.
13.5291. And the percentage error being minus 8.8891%. So write it down, then we'll talk. Okay, write it in a sheet of paper, get its fixed value in, and we'll collect it at the end of the class. Yes,
I'm just giving like a very slightly different answer for
slightly different way.
for the 3 segments.
What are you
Getting 4277.
4277.
47.
Maybe I copied wrong.
Oh, yeah.
4277 or 4278.
And I'm getting for error, I'm getting 0.024.
249. Which I rounded off to 3.
Oh, I got 2426.
Okay, that's fine.
Yeah.
No, man. Okay, so please write this down, keep that sheet of paper ready, and then we can talk. That's your class participation for today, for module 4. Okay. Please put your name on it, keep it ready, we'll collect it at the end. So, trapezoidal rule, 3 segments, 10 segments, and think about this as this is the quality of the formula, and this is the number of segments. Meaning, if you want to integrate a function, in general, you would prefer to chop it into finer segments so that your error will be small. When you go from left to right here, so you can see that in this case, the error decreases. In this case, the error greatly decreases. In this case, something goofy is going on. Okay. And the so-called low accuracy or crude method gets you decent accuracy in both cases. It's less than 1%. The Simpson's 1/3 rule gets you 10% if you use less number of segments, and very good accuracy if you use larger number of segments. The 3/8 rule gets you good accuracy, but it seems to deteriorate if you keep increasing the number of segments. Can you come up with an explanation or a theory that could explain what is going on with number 3? With trapezoidal and 1/3 rule, it's pretty straightforward. You make the segments finer, you get improvement in your accuracy. You go from a method that uses only a trapezoid to a more polynomial approximation of your function, you get improvement. That is especially here, not here. What might be happening here? I want to see your thinking on this. What might be happening in the 3rd example, apart from the fact that we could have screwed up, which I don't think all of us could collectively do. That's why I don't do anything alone. Yeah,
Would it be possible?
I'm the one who asks questions. Come on.
Would
You
it be
should be
possible?
answering.
Yeah, okay, so I'll give you a potential answer. Would it be because the reason why you tell us different methods is because sometimes they break, so you need to.
No, it's not that. It's not that they have like a kill switch or something. They all work, but they all work with some accuracy. here is data in front of you. The accuracy apparently gets worse when you go for more segments with a method. What could possibly be the reason?
The 3/8 rule treats all of the function values as if they would be approximately,
A cubic spline.
so it treats them all as if they would be approximately kind of following the same pattern. Multiplying it by 3 and also 3/8, which is slightly over 1/3. Whereas the 1/3 rule alternates the even and odd iterations, because the spline is going to vary as it goes. So the 3/8 rule is going to work better with fewer, because you're going to have less numbers of even and odds that are going to deviate from I guess it's expected range, whereas with 1/3 rule,
I think I understand what you're saying. Would you allow me to paraphrase it?
please.
So. The trapezoidal rule is very easy to imagine, okay? It takes. So no need to write here, okay? And I promise you this won't be on the test. Okay, so just listen, try to absorb it if you can. The trapezoidal rule. It takes any curve and subdivides them into trapeziums, and the error you pick up is literally this area here. And if you have a curve that is very gently changing or it's very monotonically changing, the error will get smaller as you make the segments finer. And that shows in our analysis. It gets better. If you do 100 segments, it can be as small as you want it to be. Or if you do more segments, it can keep getting smaller. The Simpson's 1/3 rule, in principle, what it does is, instead of fitting a linear, it fits a second order polynomial. So it tries to say that there could be regions where the approximation, the fit goes above the real curve, or imagine it this way. You are having a point and you're having another point. There are a million or infinite ways in which you can create or imagine segments. One possible imagination is the trapezium. Okay, another possible imagination is you have these sides to be straight lines and then a polynomial. Now, if your data did have a lot of these up and down fluctuations, these polynomials will capture it well, and you have this error sort of cancel out by symmetry. But if you have very smooth functions, you don't need this kind of fluctuations. And as you go for these higher order methods, instead of fitting a cubic spline, you might fit higher order polynomials, and it only gets compounded. So what you want to select is not blindly the most complicated method you can find, but do a sensitivity test. It's sort of trial and error, where you have methods, candidates, and segments, so that you do this. You select one problem, like a test problem for which you know the answer, do an assessment, select a method, and then use that method for your real implementation. Now, how do you select the test problem? That is very key when you do numerical science. That test problem should be very similar in features to the actual problem you will be trying. It's like if you're testing a car, your wind tunnel should simulate the conditions that the car is expected to withstand. So selecting a numerical method isn't any more different. It's you have to pick functions. Suppose I'm going to work with exponent of minus x squared type integral. So I want to compute not this, but exponent of alpha x squared multiplied by x power beta dx. suppose this is my functions of interest. What I would try to pick one case where alpha equal to 1 and beta equal to 0, for which I know the exact value of the integral, and use that to assess my numerical integration methods. So I would construct a matrix and I would come up with a rationale to say it's like you can put it like costs. These methods, as you go, there are more methods in table 21.1 which involve multiple points. So what that means is the computational cost increases with the complexity of the method, and the accuracy generally scales with the number of segments. So you want to pick something with justification which gives you best accuracy for reasonable effort or reasonable cost. This is how you select a method, because there are thousands and thousands of numerical techniques available. How do you select something for your application? First, you need to understand the nature of the beast. You need to know what type of functions are you handling. Select a suitable test case for which you know the answer or the value. Then try out different methods at different resolutions. Pick out one with justification. Any comments, questions? This is by far the most important thing I could say in this course, like how you select numerical techniques, but it won't be on the list. Okay. So for those who are doing this on the computer, I'll bring it back one more time. Okay, so here is the Excel sheet that I have updated today. It has 6 sheets that I've added now for trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, 3 segments, 10 segments. So 3 times 2, 6 sheets that I've added. Use this to cross check your exercises or your homework. Okay, you are supposed to practice. Use this to cross check your answer. You don't have to need a TA or an instructor or YouTube. You can do this yourself. Okay. Questions? Yes.
So on exam 2, are we gonna be told which rule, like trapezoidal extension, like which one you want us to use?
Oh, I just made the exam and I printed it out and kept it in my office. I might almost I might spill out the answer to that, but I won't tell you. Yeah.
You missed the exam the night before.
Exam to what?
Night before we take it.
Louder, please.
No, never mind.
So in graduate courses, when I give exams, I ask them to take it as a timed test. We evaluate that. We also give the same exam as a take home. We evaluate that and weight it 50-50. I get your instantaneous knee-jerk response and then your well thought out supposedly response. And we try to see it that way. But if I do it here, it's just a lot of work for you and me. But okay, so where are we? Okay, good timing. Let's talk a little bit about the exam. Okay, so this wraps up our module 4. We saw trapezoidal rule. We saw Simpson's 1/3 rule and 3/8 rule today. All 3 of which you are expected to know. And we also saw numerical differentiation that you are now familiar with, I think. So for the exam, as far as numerical differentiation is concerned, or any method in this module 3 and 4 is concerned, worry only about equal segments. Okay, don't worry about numerical differentiation or integration with unequal segments. Okay, so yes, what was your question?
Before you erase the Simpson 1/3 rule, is it 4 sigma f of xi?
F of xi, where I values are odd.
And then is the next one two?
2 times f of xi or f of xj, where j values are even. Just to not use I again. So let me give some more details, okay, of the eggplant. So first thing is, it's open book, open notes, calculator, internet, laptop, everything is allowed, no restrictions. You can tweet about your exam during the exam, that's totally fine. Or put it on X. Okay, expect a lengthy exam. Okay, expect to be busy for all of the 80 minutes. As soon as you get the sheet, don't jump into solving things. Look at the problems. Try to think about the time. All 4 problems are equal weightage, but all 4 problems are not equally difficult. Some are easier, some are harder. Okay, think about the strategy. Because it is open book, don't just walk in with a book. I would still recommend preparing a cheat sheet. Keep everything in one place, neat and tidy to save time. It's all about time. None of the problems will be challenging, but all of them will be time consuming. Okay. The format is going to be like this. There will be a data set, say X data, Y data. And this is common for all 4 problems. Problem 1 will be on regression. So you'll be asked to do something to do a curve fit, say y equal to f of x, fit a curve and answer some question. Problem 2, interpolation. Interpolation, again, based on the same data. Okay. So regression, what things you need to be familiar? Least squares regression, linear, quadratic, cubic, linearization or transformations. Transformations. Yeah, pretty much. Don't worry about Newton's polynomials. Any other term that I don't use here, don't worry about it. Newton's polynomial is basically a generalization of these, which I did not explicitly cover, but we went up to cubic, which is practically what we need in daily life. In all of these, you should think about how will you choose your template. For example, linear requires that you have 2 points, quadratic requires 3 points, cubic requires 4 points. So you have to think about the template. Okay. Interpolation, again we did linear, quadratic, cubic. For both of these, data may be equally or unequally spaced. Problem 3, numerical differentiation. Differentiation. We did forward differencing, backward differencing, central differencing. You need basically figure 23.1 to 3. All the formulas that you will need are in that figure, these 3 figures. Okay, that's your go-to place. Okay. Pay attention to start and end points. Meaning if you have a table of data, you cannot do the same type of differencing in the first point or in the last point as you do with the interior points. Central differencing, or for example, in the first point, you cannot do backward or central, you can do only forward. And in the last point, you cannot do forward, you can only do backward, and also you cannot do central. So you have to pay attention to that. For this, especially for this, no unequally spaced data. That will make your life much simpler. Of course, that doesn't mean I'm just going to give you X and Y and ask you to compute the first derivative. I'm not going to make it like a cut and dry problem. It will be couched in an engineering or a physics problem, like heat transfer or fluid mechanics or mechanics of materials, something which you will have to apply your general engineering intuition to solve. You can't just do this like a numbers problem. Okay. Overall, okay, let me talk about P4. Problem 4 is integration. Integration, where we saw 3 formulas: trapezoidal rule, Simpson's 1/3 and 3/8, absolute error, and error estimate. We also talked about it. I didn't talk much about it today, but you should also look up what is error estimate for each of these 3 formulas.
Question.
Yeah.
Would the error estimate formula be the same for trapezoidal or Simpsons?
No, each of those has a different error formula which you should look up or know where it is in the book. If we have time, I'll bring up the book and tell you the pages. So before I forget, for differentiation, we talked about the type of differencing. We also have to talk about order of the accuracy. Order of accuracy. So the problem statement might read something like this: calculate the first derivative using a central differencing scheme and choose a scheme which has at least second order accuracy, which means you can pick the formula which has O of h squared or h4. If you have more time, you can do more points, but at least it should have second order accuracy. Yeah.
Couple of questions. For the differentiation, we don't have to derive any of the equations on the sheet. We can just start with.
Just say I got this from figure 23.1, write down the formula and proceed.
And then for the integration for absolute error, would we be given the true value?
You might have to either compute it. It will be an integral that you can solve.
Okay.
If absolute error is asked, it will be usually an integral that is solvable. It won't be some value that is not easy to integrate. Yeah. If you want to take picture, just wait a little bit more. There are some more details I want to add. Overall, pay attention to units. Like I keep saying, this is engineering, so I place emphasis on units and being consistent. I recommend that you prepare a cheat sheet nevertheless and strategize and try to leave some time to check. And if the exam is 80 minutes, you are in say the 80th, 70 to 80, the last 10 minutes, I would check my starting point, especially if I'm stating the concept correctly, the equation correctly, I'm showing the work, the steps, and then the final answer. The final answer carries, the literal final answer carries about no more than 20% in credit. So 80% is for you providing the details of how you got that answer. I did say that you can use Excel or MATLAB to do your calculations, But once you do the calculation, that number has to be presented back so that we know what the number is. You don't have to say how you got the number. Okay, so for example, if you in regression, if you are getting sigma x squared, sigma xy, all these values, you just have to state what the value is before proceeding to use them to solve for the fit coefficient. That level of steps is necessary. If you just provide only the final answer, we will give you a 0. If there are no details, there is nothing to evaluate. You might have just Googled this answer. Okay, who knows? Okay, so we need details. Questions? Now you may take a picture. Yeah.
Can we bring in Excel sheets that have stuff on them, or does that have to be one?
Bring whatever you can. Bring it on.
I mean, can I bring the TA with me?
Sure. Can I take you to the dean's office? Any other questions? So again, I'll repeat, expect a lengthy exam which will keep you busy all to the last minute. Don't almost you can expect nothing will be like just one line that you can do in like 30 seconds. It will be a lot of work. Okay, so 80 minutes, 4 problems. Strategize. Yes.
I was just gonna ask, can you explain the order of accuracy?
So order of accuracy is, we talked about this during differentiation. It starts with the Taylor series expansion for which is the starting point of all the derivations. So what's the time?
30.
Okay, we have time. So if you talk about a point xi, and you are interested in xi plus 1, and you know that the value of the function is yi here and yi plus 1 here. You can write yi plus 1 is yi plus a lot of perturbations. The perturbations, if you write them, yi plus f dash of xi times delta, or I'll use h plus f double dash of xi h squared over 2 plus f triple dash of xi h cube over 3 factorial and so on up to infinity. So this is the first order perturbation. This is the second order perturbation. That you think about it as I have to go from here to here. I have to correct for my slope. I not only have to correct for my slope, I also have to correct for my curvature. Like when you go from, of course, here it doesn't make sense because it's a flat line. But if you think of the Earth as a globe, you're going from, say, New York to London, you have to think about that you are walking on the surface of the Earth, which has a curvature. So it's not like just drawing a straight line through space. Okay. So you have to correct for curvature, slope, curvature. Third order derivative doesn't have a name, but it's still there, and so on. So if you want to use this to derive a approximation for, say, first derivative, you would write yi plus 1 minus yi divided by h equals f dash of xi plus f double dash of xi multiplied by h over 2 plus and so on up to infinity. Now this is what I want. This is the approximation for it. The rest of it is called error.
Would that be h squared over 2?
Because I took a h away, it will be only h. So this error, the leading power of h in this error is h power 1. So that is why it's called the order of accuracy. This exponent is called the order of accuracy. So when we say get us a method which has first order accuracy, we want the h power 1, or if you see the table. So if you are using the book in electronic form, you need to go to the bookmarks, find the chapter on differentiation, and here it is, what I just said. So right here. So this is exactly what I just showed. The first derivative is the difference between the two y values divided by h plus the order of the error. So if you go to the table, the error is specified on the right here. Order of h squared, h squared, h squared. Most of forward difference formulas are order of h squared only. Central differencing, if you see here, some of them are h to the fourth, which give you higher order accuracy. So if I ask you to compute, get me the second derivative to fourth order accuracy, I would pick this formula. If second order accuracy, I would pick this, like that, okay? So you should be familiar with this figure 23.123 in and out. Because the sooner you can figure this out and select the correct formula, you'll be able to do the calculation. If you select the wrong formula, of course, whatever you select, you are expected to write it on your sheet and say what is the order of the error. If you select the wrong formula, that is the demonstration where we can see whether or not you understood what's going on here. Okay, so don't be clever and just do the calculation without stating the formula. That will also be taken as you are kind of sidestepping the formula. That makes sense. Step 1 is for you to select and write it on your sheet, because we will not see your book or your Excel sheet, no nothing. We just see your exam sheet. Any more questions? If none, I'll stop here today, and the TA